One of the best ways to gain insight into the dynamics of a system is to analyze its time response. In today's video, we look at how to calculate the behavior of a system without any input. Such a system is called a homogeneous system. In the next video, we will use this result to calculate the behavior of a system with an input, called a non-homogeneous system. The problem we address in this video is the following. Suppose the state equation is given by a homogeneous equation, which means that we use the normal state equation but remove the input term. The values of the states at some initial time t0 is given by x0. We want to find an expression for the states for all time after the initial time t0. The solution to the homogeneous equation uses the matrix exponential function. Let's first define it before looking at the solution. You should know by now that the scalar exponential function e to the at, where a is a constant and t is a variable, can be written as the power series 1 plus a times t plus 1 over 2 factorial times at squared plus 1 over 3 factorial times at cubed, etc. The matrix exponential function is a function that takes square matrix A and variable t as inputs and is defined similarly to the power series for the scalar exponential function as the identity matrix plus matrix A times t plus 1 over 2 factorial times a squared times t squared, where a squared means the matrix multiplication of a times a. To illustrate this definition, let's look at an example. Suppose matrix A is given by this matrix, then the matrix exponential of AT is given by the identity matrix plus matrix A times T plus 1 over 2 factorial, which is a half, times matrix A times T squared, etc. It is important to note that the matrix exponential function is not the same as taking the scalar exponential function of each element. With the definition of the matrix exponential function in hand, let's look at the solution to the homogeneous equation. It can be shown that the solution is given by the following expression, where this is the matrix exponential function of matrix A times t minus t0, which is the initial time, and x0 is the initial states of the system at time t0. We will prove the solution at a later stage. If the initial time t0 is 0, the solution can be written as x of t is equal to the matrix exponential of a times t times a vector x0. The matrix exponential of a times t is a matrix that we will use often. We call it the state transition matrix and denote it with capital Phi of t. If we have the state transition matrix, calculating the solution to the homogeneous equation is easy. We now move on to the question of how to find the state transition matrix. There are several methods to calculate the state transition matrix, both exactly and approximately. One can, for instance, approximate the state transition matrix by using only the first few terms of the power series definition for the matrix exponential. However, we are going to look at two methods to calculate the state transition matrix exactly. The first method we look at uses the inverse Laplace transform. The method says that the state transition matrix can be calculated by taking the inverse of matrix Si minus A and then taking the inverse Laplace transform of each element of this matrix. We will derive this result at a later stage. For now, let's illustrate the method by working through an example. Suppose matrix A is given by this matrix, We can then calculate the inverse of Si minus A as S times the identity matrix minus matrix A, of which we take the inverse. This is the inverse of matrix S minus 1, 2, and S plus 3, which is calculated as 1 over the determinant times the adjoint matrix, resulting in this matrix where each element is a function of the Laplace variable S. We now take the inverse Laplace transform of this matrix. In order to do this, we need to do partial fraction expansion, and after calculating the residuals, we get this matrix. We now apply the inverse Laplace transform to the top left element by making use of Laplace transform tables and get 2e to the minus t minus e to the minus 2t. We similarly apply the inverse Laplace transform to all the other elements. The result is the state transition matrix, which is written in terms of the time variable t. The method using the inverse Laplace transform is often quite tedious to use. We now look at the related method that makes use of the similarity transform. This is the transformation that transforms a state variable system to the modal canonical form. This method often requires fewer calculations. The method says that the state transition matrix is the transformation matrix P times the matrix exponential of lambda times T times the inverse of the transformation matrix P. Here lambda is the A matrix of the modal canonical form. We will again prove this result at a later stage. To illustrate this method, let's look at the same example as before. In a previous video, we have calculated the eigenvalues of matrix A as -1 and -2, and we can therefore write down the system matrix lambda as this diagonal matrix with the eigenvalues on the diagonal. We calculate the eigenvectors corresponding to these eigenvalues as vector v1 and v2, which means that the transformation matrix P that would transform this system to the modal canonical form is given by this matrix of which the columns are given by the eigenvectors of the system. Looking back at the method, we have P and lambda, and we can easily calculate the inverse of P. The problem is now to calculate the matrix exponential of lambda t. We do this by using the inverse Laplace transform method of the previous page. Matrix Si minus lambda is given by this matrix. Its inverse is 1 over the determinant times the adjoint matrix, which results in this diagonal form. We do not have to do partial fraction expansion, and we can directly apply the inverse Laplace transform to each of the diagonal elements, which results in this diagonal matrix. We now have all the different components necessary to calculate the state transition matrix. We have P, we have the matrix exponential of lambda t, and we can calculate the inverse of matrix P as 1 over the determinant times the adjoint matrix. The first two matrices multiplied together forms this matrix, and after multiplying with the inverse of P, we get the state transition matrix, which is the same as the one calculated in the previous example. With the calculated state transition matrix in hand, let's return to our original problem, solving the homogeneous state equation, and work through an example. Suppose we have a homogeneous system described as follows, and the states at the initial time 0 is given by this vector. The question we ask is how the states will behave after the initial time. As stated previously, the solution is given by the state transition matrix times the initial state vector. We calculated the state transition matrix on the previous 2 pages, and after multiplying with the initial state vector, we get this vector. The first state, x1, is therefore described by e to the minus t minus e to the minus 2t, which can be approximately sketched as follows. And the second state, x2, is described by minus e to the minus t plus 2 times e to the minus 2t, which can be approximately sketched as follows. By calculating and plotting the behavior of the states, we can gain a lot of insight into the dynamics of a system.